A pentagon is formed by placing an isosceles triangle on a rectangle, as shown in the figure. If the pentagon has fixed perimeter P, find the lengths of the sides of the pentagon that maximizes the area of the pentagon. So this is a multivariate optimization with a constraint. I'm thinking the most reasonable way to implement that constraint is going to be with a Lagrange multiplier. And then we'll just have, we'll have to take some partial derivatives and have a system of equations that we need to solve. I think the thing we have to think about the most here is exactly which variables we want to use as our independent variables. But as I start sketching the figure, maybe that'll be something that gets made a little bit more clear. So this angle is labeled as theta in the figure, and it's an isosceles triangle, meaning this opposite angle is also theta. That's kind of a hint that maybe theta should be one of the variables that we use to parameterize everything. I'm going to call the base of the shape x and the height of the rectangular portion y. Then the other dimensions we should be able to write in terms of x, y, and theta. Let's call the height of this triangle, that'll be h. And the hypotenuse of these triangles, we'll call that z. So I have then, this of course is going to be x over 2. I'll have tan theta is equal to 2h over x. I think what I'll do is I will have x, y, and theta be the three variables that I use for everything. So what that means is I want to rewrite this as h is equal to tan theta x over 2. And then when I write down formulas for the area and perimeter in terms of other things, I won't want to see an h anywhere. So I also need to write out z. Cos theta is equal to x over 2z. So this says that z is equal to x over 2 times secant theta. Let's write the area of this pentagon. So the area is going to be x times y. That's the area of the rectangular region. The height of this triangle, or sorry, the area of this triangle is h times x over 4, but there are two of them. So we're going to add h x over 2, but we're going to rewrite this because we have h is equal to tan theta x over 2. So we get that. There's the area in terms of x, y, and theta. And the perimeter is x plus 2y plus 2z. So this is x plus 2y plus secant theta x. All right, so we want to maximize this quantity subject to this quantity being fixed and equal to a given constant p. So I'll write out this function of three variables, x, y, theta, and I guess I'll introduce the Lagrange multiplier immediately, call it lambda. That's what we get. And I want to take partial derivatives and set them equal to 0. I'm pretty sure this is the derivative of secant theta. The derivative of secant theta is just secant tan. Just so I don't end up carrying a mistake through this, I'm going to derive that right now separately. This is a completely separate thing that I'm working on here. Yeah, so the derivative of secant is secant times tan. Okay. So I have an equation, a system of equations, 3 equations and 3 unknowns. Well, there's a fourth unknown, the Lagrange multiplier, but we also have a constraint here. And now I need to try and figure out what the most convenient method will be to solve these things. Okay, well, I see right away. I'm going to solve for the Lagrange multiplier first. Clearly that'll be in terms of x, and then eliminate it everywhere else. Okay, so this should allow us to solve for theta, which is pretty convenient. Okay, so there's the angle we need, sine inverse of a half. Oh, what does that equal to? Root 3, is this correct? So what is that value of theta that gives that? Is it pi over? Is it pi over 6? I'm not sure if the actual value of the angle will matter. What I'll care about are the other trig ratios of theta. So I'll care about cos theta, tan theta, and so on. So I'll just keep referring to this triangle. Okay, so I have theta. There's another equation up here I haven't used yet. So I know what lambda is. Let's simplify that equation there and see what happens. Okay, so that third equation from the partial derivatives narrows down to this. And I also have the constraint that I need to use, which will give me another equation for x and y. I mean, theta's in here, but we're going to make a substitution for theta. So this whole thing has to be equal to 0. Okay, so I've got 2 equations now, and 2 unknowns, x and y, which I'll try to solve. Maybe I can rewrite the bottom equation first. Okay, and the first equation is the same as 2y plus -1 minus root 3x over root 3 is equal to 0. And now if I add these equations together, no, I don't want to add them together. I want to subtract one from the other. So I get that x is equal to p divided by 2 plus root 3. And now I should be able to find y somewhat easily. I'm not sure if I have some algebra mistakes or arithmetic mistakes, but I kind of want to just check my work before going forward. Why am I getting a different answer here than I was before? Or maybe bizarre. That's not what I was getting before, was it? Well, maybe this is the same. No, it's not. What is going on? Okay, I feel like I've made so many. I must have made some errors somewhere. I really don't know where they're coming from. And I don't want to bother going through a huge amount of messy algebra. I'm going to backtrack way back and try and do this a little bit more of an organized fashion. I'm going to go all the way back to this set of equations here. Okay, so I have lambda is equal to negative x over 2. I can rewrite my other equations now. Okay, well, I found where my arithmetic mistake was. I was doing some multiplications incorrectly. But I'll just continue from here on out. Okay, so there's x, finally, after a lot of struggles and mistakes with what should have been simple algebra. I should be able to substitute back into an equation for y. There it is. Okay, there's the height of the rectangular portion. And that final side, the hypotenuse of the triangles, z equals x over 2 times secant theta. And there's the last side. So, all right, this took a lot longer than it should have just because of silly mistakes that ended up carrying through the rest of the solution. The approach was fairly straightforward, just considering the geometry of the problem, writing down the area in terms of x, y, theta, and the perimeter in terms of x, y, theta, set up a very simple three-dimensional optimization with a single constraint, and work through the equations to solve for all the variables. If I have any more to say about this one, I'll put it down in the description. Thanks for watching.